All right. Hello, everyone. Welcome to the robotics seminar. We meet every Friday at 1:30. We have several distinguished speakers. Today, really excited to welcome Chuchu, who is a professor as of 2 months ago. So freshly minted. Welcome to professorhood. So I know Chuchu from her really incredible PhD work at the University of Delaware on being able to estimate state from incredibly noisy things like cameras that are mounted on your eyes and other devices, specifically where there are constraints around power, there are constraints around the resolution and accuracy with which you need to be able to measure and estimate these state variables. And so if you look at any of the glasses that are intelligent, a lot of them, the underlying algorithms that are being used there come from a lot of her work. She's now a professor at George Washington University at the Mechanical and Aerospace Engineering Department, and has started the EPIC Lab, which is pretty epic. And Chuchu will be here for the rest of the day. I know she has a very busy schedule, but she may have a little bit of time after this talk to meet and speak with you all. And welcome.
Thank you. Thank you for the lovely introduction. So a little bit background about me. I really officially received my PhD degree like really 2 months before. And now I'm an assistant professor at the George Washington University where I lead the EPIC Lab. So EPIC stands for Estimation, Perception, and Intelligent Computing. I use all my knowledge to come up with this lab name. And so today's talk, basically, I would think 90% of it will be coming from my 5 years of PhD training, and maybe 10% will be the work after I joined the George Washington University. Okay, so robots. Today we are talking about robots. So what do we consider as a robot? So in my opinion, like anything, any AI with a physical body could be considered as a robot. Say an AR glass, I'm part of the robot family, and maybe something stand on your desk, and that could also be a robot. So let's just give that informal definition by just myself, okay? But they all share the very similar thing. First one is trustworthy, right? I always say, if I'm talking to my ChatGPT and they give me a wrong answer, I got the wrong answer. I might be okay with that. But if we are talking about a robot, if a robot goes wrong, it has a real-world consequence. In my 5 years of PhD, I break a lot of robots, and I really don't want that to happen in the future. So this is a high priority of the robotics research. And also, we care about privacy. Like, I don't want a robot that carry a camera that's walking in my house all the time. I might feel a little bit concerned about that. And definitely resource, like, robots are even better. I can put a laptop on my robot. But when we are talking about the AR, VR glasses, really there's no computing on it. You cannot put a GPU on it like now, maybe in the future you can. Okay, and dynamics. I think that's a beauty, and that's also the constraints about robots. Like say if we are flying a drone, I cannot make it just fly as how fast I want it to be able to fly. It has its own dynamical constraint. Okay, so yeah, so my first chapter will be, I believe, all the intelligence coming from state estimation. I am a state estimation theory guy, okay? All right, so the motivation behind it is all the intelligent behavior starting from answering these two questions. The first one is you need to know where you are. Second is you need to know what is surrounding you, okay? For example, I'm using this Meta AR glasses as an example. We are trying to use this AR glass to help the people with limited vision, right? So when the people is talking to the AR glass, I want to grab a green apple, right? The AR glass first need to know where you are in this grocery store, and then it can guide you, okay? So you go straight and you turn left, and then you might see a green apple, and then it can guide the people to grab the green apple, okay? So answering these two questions are fundamental for the intelligent robots, okay? But how do we basically give answers to that? Especially given the GPS-denied environment, like robots in the Mars, how do we know that, right? We definitely use onboard sensings, right? So the first sensor we use, camera. We are using cameras as the eyes of the robot. The good things about camera is it's cheap, okay? And it has high resolution. It gives you a lot of information from the environment because you have this really dense visual information. But the problem is, first, it's scaleless. So single image, you cannot tell the object is far away from you or is close to you, okay? And it is also lower rate compared to the other sensors. It's also sensitive to, say, lightning and dynamic object. Right, so today I want to introduce another sensor we call IMU. So pretty much like us humans, right? I'm not just relying on my eyes to interact with the world, right? Even though if I'm close my eyes, I will not lose my balance. Even though I close my eyes, I can still touch my nose, okay? Similar to this little kid being a spint, and then the kid cannot stand is because the inner ear got interrupted. Okay, so when we are talking about the robot, it is a sensor called IMU. It is basically a combination of gyroscope and accelerometer. So it feels you the dynamical information of the robot itself. It also sends you the gravity direction. And nowadays, all the mobile phones have these IMU sensors. It's also very cheap and very high frequency. The problem is an IMU is super noisy. It can be drift and has a lot of bias. Okay, so we do believe that the visual inertial sensing is a really, really good combination. The cameras are the eyes for the robot to see the world, and IMUs basically sense the own dynamical information of the robot itself. And the most important part of this is these two sensors are both cheap, and cheap in terms of US dollars and also in terms of computation. And also these are lightweight sensors. So any robot and device should be easily equipped with those two sensors. All right, so a little bit of the math behind these two sensors, right? We are definitely modeling the sensor, okay? So for example, here the IMU is measuring the linear acceleration and angular velocity. And then we have this continuous time inertial kinematics model for the IMU. And for the camera, here I'm just showing us very simple pinhole camera model. Basically, we are projecting the 3D feature point in the environment to the 2D image, and then we can leverage the spatial translational information to formulate these measurement functions. But the state estimation problem, right? So we are modeling the sensors, and then we are leveraging the raw sensor input as input. And our goal is to use these sensors' raw measurement and our model to estimate the state. Okay, so here I'm just using an example. The state is a quaternion, which is a rotation of the robot from the robot frame to the global frame. And we also estimate the position, velocity, and other state that we care about for the robot. Okay, this is setup of the state estimation problem. Okay, so yeah, again, given this problem setup, we are given the readings from different sensors. Here I'm just using camera and inertial as an example, but we are keep receiving the image input, and our goal is to use those raw measurement to estimate the state. We are formulate this as a probabilistic state estimation problem, where we are using x to represent the state that we are interested in. So here, for example, we're interested in the orientation, position, velocity, okay? And x hat is our estimate, because we never know the ground truth. Okay? We are using our estimation algorithm to estimate our state. And what is this P? Covariance, right? So this is a Gaussian distribution. If it's a 1D, it's just a variance. We have a mean and the variance. And it's a multiple dimensional state variable. So we have the state estimate, and it is corresponding covariance. So this covariance represents the uncertainty of the estimated state. So problem set up. All right, how do we solve it? So basically, given the different nonlinear measurement models, we have different state estimation algorithm to solve it. For example, we have filtering. So filtering, we just linearize this nonlinear measurement. And for example, I can use the inertial to do the propagation and use the cameras to do the update. If I have a LiDAR, I can use LiDAR to do the update. If I have another radar, I can use the radar to do the update. I can also just do a setting window optimization. I just collect all the nonlinear measurements in the setting window and then solve it iteratively. okay? And that's basically the state estimation algorithm. And filtering is approximate equal to a single-step optimization. There is an argument on which one is best and which one is better. Yeah, so these are the basic algorithms, okay? All right, and next, which is a big part of my PhD work, is we know we are doing state estimation, right? We are trying our best to using the raw sensor input to estimate the state. Sensors are noisy. My measurement model are inaccurate. This world has so many things I cannot predict. Estimation will never be perfect. How can we still trust our estimation result? It's a question we ask. Okay, so here I want to introduce you how do we evaluate the estimation performance. First thing, accuracy. So here I'm just using a simple example. So this is XYZ 3D position, okay? And X, that top one, is my true robot, where is true position at, okay? And X hat is I'm using all the sensors and my knowledge to try my best to estimate where my true robot state is, okay? So the accuracy by definition is how good I'm estimating compared to its ground truth, where I never know the ground truth, okay? And I want to introduce another terminology called consistency. So consistency by definition means my estimated covariance should be equal to or larger than the true covariance. So what does covariance mean conceptually? Okay, so this means the uncertainty bound that represent my error from my estimate and the true. So a consistent one means that, okay, now it can bound the true error. Because remember, we are also estimating the covariance. We never know the true covariance. So let's see what will happen if I do not have a consistent covariance estimation. So this one, the red one, is an inconsistent one. So what does this red one mean? It means my state estimation algorithm is basically telling me your state estimate X hat can be anywhere in that red epsilon. But my true state is outside of that. Then if there's another robot coming in, it might hit directly to the region it trusts it should be. Okay, so it basically tells you your estimator is lying to you. You cannot trust it. So consistency is super important when we are doing state estimation. And
clarifying question. I guess like there's some form of min-maxing that probably needs to happen in that, like, if I wanted to produce a consistent covariance, I could produce one that is huge,
Yeah.
like vast. So really, we want the best covariance that is consistent in some way. Sorry if I'm like going ahead in your talk.
yeah, that's a great question. So a really good covariance estimate will be just bound the error. And I directly know that's my true covariance, but it will never happen. So we want to be a little bit conservative rather than overconfident. That's safer. Okay, so that means basically you cannot trust your estimate. So if you have something being estimated there, but you cannot tell how good or bad it is, you cannot trust it. It can be super good or it can be super bad. You don't know. Okay, so this is super important. The other thing we find is it will directly lead to inaccuracy. So here we just simulate a simple 2D example that one is consistent, the other is not. We also directly see that if it's not consistent, it will also be not accurate. So to evaluate an estimation, we need to consider both the accuracy and also the consistency or the uncertainty estimation. All right, go back to the visual-inertial navigation problem we just talked about, which is a big part of my PhD. What will make the estimator inconsistent? So we here have we see an issue called observability and inconsistency. So what does that mean? So observability analysis basically is given this sensor and given the state that you want to estimate, no matter how many times you measure it, you can never recover the state. So say I'm asking this scale, what is the temperature? No matter how many times I ask, it will never tell me the temperature. If I'm just have a camera to see an object, I'm saying, oh, how much do you weigh? I might have some prior if I'm given a lot of initial training data, okay? But fundamentally, it's unobservable. And why it happened in the visual-inertial navigation system, okay? So it is not a fully observable problem. Okay, so what we are doing here, we take a look a little bit more detail. So we define a global frame of reference. That's where we get started. Okay, and then as a robot move, I'm moving to another location. I'm estimating myself with respect to that global frame of reference. But the issue is, if I have a camera and I have an IMU, my camera is seeing myself and the world relative to me. And if I have an IMU, it measures my acceleration and angular velocity. It measures from my current position to the next position. I never ever have the measurement directly to that global frame of reference. Okay, so we proved that because neither sensor directly measure the global pose. Okay, so we proved there are 4 degrees of freedom unobservable directions corresponding to the global position and global yaw. The other 2 rotation is being constrained is because of the gravity, by the way. This is a real-world system, has 4 degrees of freedom unobservable directions. And then we are building our state estimation on top of that. We found that the unobservable direction goes from 4 to 3. And this caused the inconsistency. It's one of the biggest reasons caused the estimator being inconsistent. Okay, so there is an observability mismatch issue that my state estimation algorithm didn't really capture the true property of the real-world system, and it caused the issue. Okay, so we do have a lot of work along that line. We fix this issue, and we improve the consistency with some theoretical guarantees. And it is broad applicable to different estimators and different problems. You can imagine this is not just a problem for the camera. The LiDAR also just measure you from your current position to the whatever you are receiving, okay? So this, and also relative robot estimation is also an issue. So it has a wide application to different problems and estimators.
I have a question about that. You talk about these 3 degrees of freedom being unobservable. When you have an algorithm that runs, one can have different guarantees about what it does with the unobservable degrees of freedom, right? Like you can say, well, it's going to project, or it's going to let it wander about, like, uncontrolled. Are there different algorithms that make different, like, implicit or explicit assumptions about what they can't observe?
If I understand the question correctly, it's asking the algorithm itself. So
yeah, I mean, I guess like there's like different state estimation algorithms. Like you can have a particle filter, you can have an UKF, you can have all of these different algorithms. Somehow they're giving us full 6-DOF solutions.
Yeah.
So they're making something up about the other 3 DOFs.
Oh.
I guess the question is, what do they make up, and is that consistent? Does that matter?
That is also a very good point. So even though the global frame of reference is unobservable, we can still estimate the pose. We see this. We are still keep running our VLO algorithm to estimate the pose. And that's because only the global frame is unobservable, but all the relative can be observable. So we can still really track the pose as long as we fix the global frame of reference. And we do not have this observability mismatch issue. Then all the algorithm didn't make up anything, it's just naturally solvable once we fix that global frame. And I will cover a little bit on how do we do that later.
When you do your observability analysis, since you're like a nonlinear function, what did you linearize about to get to your like O matrix?
That's a really, really good question. So we do the observability analysis. So for the nonlinear one, we do for the real world system, and we prove that's 4 degrees of freedom. And here we do the linearized one, because all the nonlinear estimators we are developing right now are built on the linearized model. So we do linearize the nonlinear function and then use that C, you see that Jacobian matrix, to build our observability matrix. And that is linearized with respect to the x hat that is the current state estimate. Now using that, we prove this is 3-DOF unobservable direction. And actually, we fixed that Jacobian. You can also consider that A is Hessian information matrix. We fixed that Jacobian to make these 3-DOF match the 4-DOF. Okay, and here are some results. So this is our proposed algorithm. We fixed this problem, and you can see those dashed lines are the bounded covariance. And we run thousands of multicolor simulations, and our estimation error can be bounded by that uncertainty compared to the standard. And we also greatly improve the accuracy. Okay, and another interesting part is we want a real-time state estimate, and we also realize this covariance or this uncertainty is super important. But for many algorithms, for example, like this, getting this covariance in real time is not trivial. Because if we are talking about the optimization algorithm, we maintain an information matrix A. And to be able to recover the covariance matrix, we need to do an information matrix inversion. That can be quite expensive. Okay? So we also develop an algorithm to make the covariance estimation faster in real time, because if you're considering the downstream applications, we need real-time uncertainty estimate to support that. Okay, so in summary, this is a really big part of my PhD work. Every component of the robotics is imperfect. So we have these noisy sensors. Everything is imperfect. And the ground truth is never available at the decision time. So when we are talking about robot, the robot is acting on its estimated state and the environment. So everything is grounded on its estimation. And a robot, in my opinion, is as reliable as the uncertainty is acted on. So not just accuracy is important, uncertainty estimation is also super important. All right, and next I want to talk about efficiency. Right? So robots need efficient algorithm. So this is a motivating example. So this is in collaboration with Meta. So the XR example is, so for those devices, we really need energy efficient, numerical stable, ultra fast ego motion perception. And I will skip all this related work, but there are a lot of existing state estimation algorithms, but all of them lack of efficiency on those devices with extreme swap constraints. And they will also face numerical issue when you cannot run 64, when you have to run 32 on those devices. So this motivates us to maintain not a full covariance matrix. So this is super dense. This means that it's full of numbers in this covariance matrix. We don't want to maintain that. We want to maintain part of it, a upper or a lower triangular of the covariance matrix, because it can represent a better numerical robustness, and it has smaller condition number. It also guarantees the semi-definite positive conditions. Right? But I will say traditional square root filter, even though we are not the first to develop this square root filter algorithms, traditional is still inefficient with the Visual-Inertial setup. So basically, when you are doing this operation, at the end of the day, you cannot keep maintaining this structure. And at very last step, you need to do an extra QR decomposition to recover this really nice lower triangular structure we want to have. So this is our award-winning square root filter algorithm that we directly maintain an upper triangular structure during all the operations. And we do not need to do this extra QR, and so that we are super efficient. I also want to comment on their very special design of the square root filter, VIO, powered by our good old-fashioned engineer that we care quite a lot. So this is our algorithm architecture. And I want to highlight that we are doing marginalization. Marginalization means that we cannot maintain all the state in my algorithm. We have to, as I'm moving, especially I'm moving super fast, I cannot keep all the memories, everything I've seen before. So I have to do this marginalization smartly to remove the information that I don't need. And in our square root filter setup, marginalization is important in terms of state ordering. So for example, if I put the state order in the wrong way, I need to do an extra QR to get that upper triangular. But if I do it in the correct way, when I want to marginalize state, I don't need to do that extra QR. And there are some results. So our method is 2 times faster than the state-of-the-art, and we can run over 900 Hertz. And our most recent work just being submitted, improve it to make it even 2 times faster. And some work that I'm wearing these meta glasses and really stress test it by giving it really crazy motions. I think it works super fine. And we can see the trajectory is quite smooth. And compared to the other method, we are doing a lot better. So the next question is, even though we are using camera, even though we are using all these sensors, the question is, does the robot really need to see the entire world, right? So the motivation here is data transfer is actually quite expensive. So this is the analysis that Meta does. It shows in the SLAM that data transfer costs almost 80% of the power. Transfer means we are transferring the image from the front-end sensor to the host processor. Okay, but like say we are developing all these, good camera, high-quality image. It's for us human, right? We want to see a nice picture. But for the robot, does it really need to see that, especially given this code consumes a lot of power? So my answer is no. Oh, this video is just for fun. It shows that the robots are being hot after it works, so people are cooling it down. I don't think this is because of data transfer, though. I think it's because of the joint encoder of the robot. But for the AR glass, we do feel a lot of heat generated because of data transfer.
Question. When you say that you're spending all that power on data transfer, is there a computer that's in the glasses?
Yeah.
And okay, so you're just like transferring images from camera to just the computer?
Yeah, computing component. Okay, so this part, I'm in collaboration with my awesome ECE department colleague. So don't ask me anything about this. So basically the motivation is we really don't need to generate image if the goal is just to localize the robot, because the feature is good enough. Just the sparse feature descriptors is good enough to localize the robot. So really don't need the entire image. But there are some interesting parts when I'm collaborating with my awesome collaborators is which part you need to put on the near sensor computing and which part you can really put on the host processor. There are some really interesting discussion there, and I think I'm really proud of this work. But what I can tell you is the quantized VIO estimation part, because that is my domain expertise. Okay, so here we want to leverage really low bit information, not even the traditional one. So we do develop this quantized estimator, and we show that we can use one single bit to be able to generate good enough estimation performance. I will not say as accurate, as good as the use all the information, okay, but it's good enough. So we are comparing our algorithm to the traditional one. We demonstrate 900 times better of the bandwidth because we don't transfer the full image. We just transfer the feature descriptor, so that is reasonable. Okay, in summary, when we are doing those locomotion, and especially on the swap constraint, we really need real-time and energy-efficient performance. And if you need ultra-fast post-estimation, please try our open-source square root filter. And also, I do think the estimator to sensor co-design can be super interesting because it really need to design both on the algorithm side and the sensor side. Okay, next one. How should we represent the state? We talk about a lot on state estimation, but we never really touch on state representation. So, right, traditionally, like as I mentioned before, we are defining a global frame of reference. Then my robot is a moving frame, and I'm estimating myself with respect to the global frame of reference as I'm moving. Okay? So, and we discuss a lot of the observability issue. This is not good. And in reality, what we do is we do have an initialization algorithm to initialize that global frame. That can be time consuming. Right? So again, I'm using this meta AR glass as an example. Like, I don't want the user to grab the glass and initialize 1 second and then start working on it. I want it to grab and leave. Okay. This is very challenging. So we do have some work on how to make it super fast. And compared to the baseline, our method reduced the state size and this be able to run super fast than the traditional 1 sec algorithm. But we talk about the global-centric representation, which I'm initializing the global frame, and then I'm estimating the robot relative to the global frame. It has observability issue. But is that the only representation we can leverage? And what if I don't even have that global frame of reference? I directly estimate the relative motion, right? That can be a solution. So in fact, that is truly not the only solution. We do have this robot-centric representation. As I said, I'm estimating everything relative to the moving robot frame. Okay? Just when we are plotting that as a trajectory plot, we still need to transfer those back to the global frame so we see a trajectory. Otherwise, we cannot visualize it. And we do have some other representations, say invariant representation, and also mitigate this unobservable issue. So the hidden constraint here is different representation will affect the system property quite a lot. So we change nothing. The estimation algorithm is the same. We do the same common filtering. We just change how do we represent the state. But the estimator property got changed. This is quite interesting, right? So we just tweak how do we represent everything, and it magically become a little bit better or worse. And also the hidden constraint is right now the state and arrow state are sharing the same representation. So if I've defined my state in the global frame, I mean the arrow state is also in the global frame. And we show that that is not the only choice. And we also unify this different representation. And we introduce a new representation that I'm developing a state representation that is representing everything in the global, because I do need that to better understand this robot state. But for the arrow state, we can have the freedom to design a new one that can have the property, the nice property you want. It can be related to consistency, efficiency, or even accuracy. Yeah. Okay, so representation is a huge issue in robotics, right? So when we are talking about, especially for these 3D rotations, I assume you are all, suffer from these. So different system will have really different representation. And what I do is just try it and try to rotate 90 degree, 180 degree to see if it works. But the representation is super important in terms of the estimation. A little discussion here is state and arrow state representation can actually fundamentally change your state estimation algorithm property and the end performance. And the second bullet is no free lunch. Right? Sometimes some representation have better, say, efficiency in certain scenario, and in some other scenario, it doesn't work. Right? So I don't believe, or I cannot find a uniform best representation for every scenario. So I do believe there's no free lunch. And also, understanding the physical meaning is important. For example, this is one representation that is super popular. What does this mean? It's some small rotation, small orientation, okay? Second one, I'm multiplying some left Jacobians with respect to my arrow position. It seems like some orientation multiplier position don't have very good physical meaning. Some orientation multiply my velocity, something multiply my feature position. Okay? So it doesn't have a really good interpretation that you can understand for this. And we do need to have and we as human need to have a good understanding of what does this mean, because my uncertainty is associated with this. It better represents something in the physical world. Okay. And the next one, we are dealing with robot. We don't want just a robot to be able to estimate its motion. We also want a robot can estimate itself. So like humans, right? So when we are aware something is wrong, if I'm off balance, I will adjust my body to slow down and to make it better. So we do also need this capability in terms of robots. So in different aspects. First is a robot. Here, for example, we are equipping with multiple sensors. We have LiDAR, we have GPS, we have wheel encoders, we have cameras. Sometimes when the robot is doing the longer mission, say in the Mars, we cannot just get it back, and if it's going wrong, I cannot get it back and then calibrate in my lab. Oh, where you are, where is your LiDAR, where is your camera? That's almost impossible. So we want to make all these happen online. So as the robot is moving on the Mars, and it can know what is its sensor extrinsic between each other, because this will affect quite a lot of different types of tasks. And we also have a drone parameter online estimation. The drone have a quite different frame of reference, have inertial, have body frame, have word frame, center of mass, all these, and also have all these dynamical parameters. And how do we, estimation problem can also be formulated to estimate all these parameters online as the drone is flying. So as it is flying, we can do this online parameter identification to estimate what is the dynamical parameter and also the sensor extrinsic, intrinsics online. Okay, finally, estimating the word, right? So here, traditionally, I mean 3 years ago, for example, we are doing this sparse geometry representation. That means as a robot is moving, this is a simultaneous localization and mapping problem. As a robot is moving in the environment, it is estimating its own trajectory. It is also estimating, say, the sparse feature point in the environment. And from there, the little work we do is, okay, from those sparse feature point, we can also infer or estimate a plane feature, because plane is super important. As here, I show a still-based example is I render a teapot on the table. So it's an AR, VR application. I could render some virtual object on this plane feature if I know it's a plane feature. And then we have this, very recently, we have this dense neural point map. The problem, it is offline. It is not real time traditionally. And we are trying to use our strong motion prior and also those geometry, nice geometry feature, which provide you the matrix scale and the depth to boost it, to make it faster, to make it the real-time online system. This is my lab, by the way. And yeah, we do this test on the Unitree robot, and compared to the LiDAR scan, I think our algorithm is performing quite okay, and it can run up to 10 FPS on a Jetson device. Okay, so in a summary, we want a real-time perception in a SLAM way. We want to both estimate the pose and also the environment in real time. And here's a trend. 3 years ago, we do sparse geometry, and then we have this nerve representation, and then we have the 3D GS, and eventually nowadays we have this dense neural point map. And I want to say that a strong motion prior and some classical geometric feature point can really boost the performance in many different aspects. All right, so in summary, robots, this is my belief. Robots act on their belief about the real world. So everything is grounded on state estimation. I took this probability distribution. So this is the belief of the robot. So it is our state conditioned on the measurement and the past state. So it's always state estimate because we never know the ground truth, right? So estimation is an interface between the perception and action. And estimation is never, ever perfect, and it should be reliable and efficient. And how to enable a reliable and efficient estimation depends on uncertainty, state representation, estimating not only the pose, but also the robot itself and the world. Yeah, so from a Slimer guy point of view, these days when people ask me, what do you do? I say, I do SLAM. Their face is like, I'm sorry. Oh, you do SLAM, I'm sorry for you. Because SLAM is difficult. It's a lot of math behind the SLAM, and it's not easy to do. Okay? But I do believe that there are a lot of things that behind the SLAM are the lessons I learned, because it's grounded on this nice probabilistic estimation theory. So first, robots need multi-sensor input. Right? Definitely camera enough. A camera is not enough. And I want to say IMU is a good one. It's cheap and it gives you a lot of information. And accuracy and uncertainty are equally important when we are talking about robots. And lastly, I think there's no free lunch. I realize there's no single representation that can be good for everything. I feel we always need to trade off something to win something back. This is basically the lessons that I personally learned. Okay, and talking about the future work, first one, there are some future work that I believe I'm interested in, is active. So I think if we are going to let a robot do some mission, it needs to actively do things and actively explore the environment to infer the state and the physical properties. Otherwise, it will be unobservable. Okay, and second one is the interactive. So as I mentioned, I think if my goal is to estimate the mass of the chair, just by looking at it, I might have some good prior, but I never have a good estimate of how much it really weighs. I do need to have some sort of interaction with the object so that I can recover the unobservable state, which is the mass of the chair. Right? And I do want to thank to all my amazing collaborators when I'm doing my PhD, and then my collaborators at GW who drew that figure of that sensor. I never understand. And myself, I'm the only person in the EPIC lab right now. I hope my students will join me soon in the near future. And all the funders that used to fund my PhD work, if you are there, please keep funding me in the future. And these are my publications during my PhD. And thank you.
We have time for some questions.
When you're modeling your robotic extrinsics, for example, I was curious on how you're propagating a prior. When you're modeling your censored extrinsics, what are you using as a prior? Is it a random walk or
The prior, the extrinsic of the sensor. You are talking about, say, I have two sensors. I have one IMU, I have the other IMU. I need you something to get started, right? I do sensor calibration first. I do need to do this sensor calibration before I start the robot. And this sensor calibration, we are developing a tool, by the way, for multi-sensor calibration to be able to let you run some simple algorithm by checking the Ruko tag, for example, and then you get the extrinsic information of the two sensors.
Thanks for the great talk, by the way. It was really, really great. You talked a lot about being able to leverage metric information, whether it's IMU, whether it's cameras. certainly your tracking features and everything. But one of the things that I've really enjoyed over the past few years is the ability for us to semantically understand the world so much better. Just open world semantic understanding. You can point a camera at the scene, you can say where the chairs are, where the tables are. How do you envision leveraging that semantic context in your algorithmic work?
Yeah, so that's a good question. So I assume now that there are some network can just train, say, the depths, matrix depths, and from my experience, that's not accurate. But semantics, so for example, if I see an object, if I have one feature on that object with scale, I know the scale. So this is a cool thing. I can use just one pixel. If I be able to know that, everything's solved. So I think that is something doable. I think that's very interesting.
I guess specifically, when you're tracking in the presence of moving or movable objects, then you can potentially use the semantic priors, whether it's like, if you're in a self-driving scenario, whether there are other cars or pedestrians or any of the other NPCs, you can potentially have different models of their own motion as well as their own estimation,
Yeah.
which could be useful, right?
Yes.
Cool.
Yeah, thank you for the great talk. It just came late because of traffic, but my question is twofold, right? The first one is, you said something about when they put the glass on, they shouldn't wait for a second or some time. I mean, for some task, I don't mind waiting, right? I can just wait. If I can get a better initialization through GPS or one or the other, if that can give me the better performance, I can wait. So have you considered chances where instead of trying to improve it, where you just work on the state of the art right now and tune it to the target customer? So I work for Boeing, and we work with the defense, and sometimes it's just get the thing working. You don't need to make it perfect.
Yeah.
So from that sense, how have you tried to improve on your work based on current available techniques? For example, you can use like FFT, right, to throw most of the data, image and bring it back, so you reduce a lot of the content. Like that can simplify your work. And then the second fold is, how do you plan to use like agentic AI or the age of AI or physics-informed AI? Like I'm taking a class right now, so shout out to Dr. Heckner in my class right now, but you can use physics-informed AI to improve your performance by a lot. So how have you thought about integrating that into your work?
Yeah, so the first one, right now, maybe not right now, they might improve because they are my founders. So they ask users to put a tag on the wall. A Ruko tag, you saw that tag before? They ask the user to put that tag on the wall and then use that to initialize. That means the user needs to, first get a tag, then put it on the wall, and then do the initialization procedure to have a good initialization. That is very stable because we have a tag, right? But I don't think that is the state of the art, and I'm thinking I might create a state of the art to make it work better, to answer your first question. And second one is, from my talk, you must have seen I'm not an AI person in your definition of agentic AI, but I do think this can boost the robotics performance. And I do have some interesting directions that current capabilities of the classical traditional method hit a limit. In that way, the AI should help. Right? Say, all my sensors fail. What I'm going to do? Traditionally, the robot just failed there. But with the power of AI, it can learn something from the previous information and can at least make it not fail. That's one thing I'm thinking, to make the traditional method perform better. Second is definitely make it perform even better, right? So I have this hope. Because on my PhD, I'm always fix things that doesn't work. Today it doesn't work, I'm going to, do something to fix that. The other day, that one doesn't work, I'm going to fix that. That's kind of the research journey, But I do hope and I do believe that in the future, the robot should learn by itself and it can self-improve itself, and I don't need to be the person to fix it. It will just improve itself and make it better.
All right, thank you.
So I work on manipulation mostly, and in manipulation, at least, and learning-based approaches to manipulation, and a lot of them are end-to-end, right? You go pixels to torques or pixels to whatever. But are these methods useful in that setting too? Is it? And the reason to ask this is like in some cases there's like not a clear definition of state, and so like how should we think about state in like those kinds of problems, and how might we use some of these ideas in those settings?
So I will just give you one example. Not necessarily related to manipulation. I'm not an expert on that, but these days I'm collaborating with a thing called word model. It's a word model. Basically, you input some observations and input some state. Right now, everybody treats that state to be a known input. But how do we get those state? It's coming from sensors. And we need to come from the sensing perception, then we recover those state. I think this is one way that our state estimation guy can contribute to the all these AI method. Yeah.
Maybe the difference with the world modeling is that your latent dynamics is also unknown.
Yeah.
So like as in you're assuming known models of the dynamics, and in those cases it's data-driven models, but it's like similar filtering methods. Yeah. Is that kind of the way to think about the
Yes.
connection? Makes sense. Thank you.
Thank you for the talk. If I understood your slides correctly, is it true that the visual features are appended to your state estimate?
Appended to my state. Can you explain that a little bit?
Yeah, so you're estimating like the position, orientation, and then I think I saw on one of your slides like visual, like a feature position. Is that true?
Yeah. So we estimate. Look, simultaneous localization and mapping (SLAM) is we are simultaneously estimate the robot's position, orientation, position, velocity, and also the environmental features. So
Okay.
we do keep the feature state in our setup.
Okay, so I guess my question then is there a pruning procedure that goes on to make sure you don't have like thousands or millions of features that show up in your state estimate?
Exactly. So we call it marginalization. So marginalization means we are selectively picking the I would not say useful list, but not that useful information to get rid of from my state estimate. That's so-called sliding window estimation. So we only maintain sliding window, and so I'm keep shifting my sliding window, and I also selectively remove the feature point outside of the window. So that's not active anymore, and I will not keep updating and estimating that. But once it's being matured, right? So I've seen those features for many times, and those estimates are good enough, then they are safe to be removed. And then I'm keep estimating the newly coming in features, measurement, and states.
Okay, thank you.
In your original camera or your observation model for the camera, I think the very start of the presentation, you modeled like there was a variable for both bias and noise. So in that visual-inertial navigation example, did you end up modeling bias?
Oh, good
your
question. The bias is for the IMU. It's not for camera. Then we do estimate the bias.
But it gets added to your state space and adds more degrees of freedom.
Yes, but that's important because this is very tied to this specific sensor because IMU is super biased and noisy. And we figured once we are modeling that bias, its performance are being better.
All right. Well, thank you so much.
Thank you.